about covariance. So suppose you have two random variables x and y, and we are not going to assume that they're independent. There may be some relationship between them, some mild relationship between them. Okay? If such a thing is true, I mean, for example, if y is like some number times x, and then there's another random Gaussian noise like that, where epsilon follows some normal distribution, right? Then even with this noise, these two things will be somewhat related, right? In fact, this is like the basic model or assumptions that people use to model two somewhat related random variables, assuming that there's some kind of noise. Okay, so that there can be two random variables who are not exactly a function of the other, but nonetheless there could be some kind of a correlation between them. Okay, so if you have such a case, we're going to define the covariance of x comma y as the sum of x minus x bar times y by minus y bar divided by n. Yeah, actually I should really do xi. So yeah, I'm a bit mixing up the actual samples and the random variable itself. Okay, so let's think of it like this. Let's just say that xi and y are the populations of x and y, okay? And they have the same size, and then it's a paired data so that xi and yi are from the same individual, okay? Yeah, so in that case, the formula for the covariance will be like this. If x and y come with some probability distribution, the formulas will be more complicated, but I don't want to talk about that one. Okay, so let's see what this formula is saying. It's saying that if the population size is capital N, it's like taking average of something, dividing something by n is like taking an average, right? And you're trying to see whether each individual values are above the average or below the average. You just want to know that value, and you're multiplying them. Now notice that if xi is above average and yi is above average, this quantity will be what? Positive, right? If xi is above average but yi is below average, this quantity will be negative, and so on and so on. If they're both below average, what happens?
Positive.
It'll be positive. Okay? So if x and y are distributed something like this, so that, see, average value of the x will be somewhere here, right? If you project everything down to the x values and you look at the x values and you take the average of the x values, the x bar will be somewhere here. Do you agree? Right? And do the same thing if y values are projected and you take the average of the y values, y bar would be somewhere here. And for each of these paired data, you compute xi minus x and yi minus x, and you see that things here are both above the average in terms of x and y, right? Things here are both below the average in terms of x and y, right? The x coordinate value is below the average, the y coordinate value is below the average. So in all of these, other than maybe a few things here which might be a little random, most of the things that have this kind of trend will give you positive value for the top. Do you agree? Right? So things that have this kind of trend will have positive covariance. Right? On the other hand, if you have a scatter plot that looks like this, then let's think about what that does, x bar and y bar. I think y values have average somewhere here, x values have average somewhere here. And then you can see that things in here will have x coordinate higher than the average, whereas the y coordinate will be lower than the average of the y values. So this thing inside will be calculated to negative value for these things, right? So there are a few places in the middle where it might not be so easy. So for example, this will be positive because this is both above the average, right? But you can see that in most cases, the values will be negative. So if you have a trend that's going that way, you will be expecting that this value will give you negative. So it kind of makes sense why you would be interested in this, right? What if it's scattered all over the place? Then some will be positive, some will be negative, so they're going to cancel out, so this will be close to zero, right? So if two things are somewhat independent of one another, then this will give you zero. Is that fine? Okay. So in general, this is what covariance of x and y would be. And this formula is more generic. It's applicable for the case when you just have a probability distribution for x and y, not as a discrete probability with some values given. So for this one, it's really taking the average of x minus x bar times y minus y bar. Okay, so that would be a better definition. And it agrees with this, because E, what does E mean? You're taking average, same thing, dividing by n. And if you were to expand this around, it will be what? E of x times y minus x bar times y minus y bar times x, and then minus x bar y bar. That's what's going to happen. And then you can expand this further and say this is E of xy minus E of x bar y minus E of y bar x plus, oh, sorry, this should be plus average of x bar y bar, but average of a constant is constant. It's always this value, so the average is this value as well. Okay? If you have any constant, these are constant values obtained as the average. So these are values, so these can come out. Whereas x and y are random variables, so they change, so you have to take the averages. So if you do that, you get E of xy minus E x bar E of y minus y bar E of x plus x bar y bar. But then, what is x bar? X bar is really E of x. That's what it means, right? Y bar is E of y. So if you rewrite these bars into this format, you see that all of these three are exactly the same thing, right? So you're going to end up with e of xy minus e of x, e of y. Okay, so it's a nice formula to use. Covariance of x and y is exy minus exey. A few observations. So first of all, if you had x and x, then you have xi minus x, xi minus x bar, right? Because you have x for both. Then, since these are exactly the same, it's a square of itself. And the formula for covariance of x and x is now going to look like exactly the formula for the variance, right? Because variance measures how far it's away from the mean. You square it to make it positive. You take the average. That's what variance is. Variance. And this will be true in general, that covariance of x and y will all, so this is always true. Covariance of x and y will always be equals to variance of x and x. And then if you look at this formula, covariance of xy equals to e of xy minus e of x, e of y, which we just derived. We just derived it from here, right? Then if you have covariance of x and x, what is this? This is covariance of x times x, so that's e of x squared minus ex, another ex, so this is ex squared, right? But this is formula that we have seen before, right? What is this?
Variance.
This is the variance. That's another formula for the variance, right? So you see that this formula we derived actually contains this formula as a special case when both x and y are the same. Okay? All right. Another thing that you should observe is that what if x and y are completely independent? Then what becomes of this? We've learned something about it. If x and y are independent, what is e of xy same as?
E of x, e of y.
E of x times e of y. So this is going to be 0. And you can actually say it in reverse. We say that if covariance is 0, no, I don't think you can do it in reverse. All right, so that kind of shows. This shows that if two random variables are completely independent of each other, the covariance will be 0. So it really does give us an idea of how related two things are. So it's a nice quantity to have. You compute the covariance, you know how related two things are. If it's positive, it's generally trending along with it. There's a positive correlation. If it's negative, there's a negative correlation. Now the only problem with this is that the covariance is sensitive to the units. So here's what I'm trying to say. You want to have something that's normalized to say, oh, if this value is close to 1, that means it's high correlation. If this value is close to 0, there is not much correlation. But you see, x and y have units. N doesn't have a unit. That's the number of elements that doesn't have a unit. But xi, x bar, yi, y bar has units if it's from a real-life example. So for example, if these are weights, then it could be measured in pounds or kilograms and stuff like that. And depending on the way you measure it, the units of the covariance will be different, right? And the value will change as well. So if you measure something from pounds to kilograms, 2.2 pounds is 1 kilogram. So if you measure something with a kilogram, suddenly these values will be smaller, right? So you will have a different value of covariance, which is not ideal. So what you want to do is you want to take the covariance and divide it by how this thing varies. You normalize stuff so that there is no unit. And the standard way to do such a thing is to use the z-score, right? So instead of xi minus x bar, you want to use xi minus x bar divided by the standard deviation of x, okay? And then you do yi minus y bar, and you divide it by the standard deviation of 1, and then take this quantity and divide it by 1 over n. And this makes more sense because now these are normalized. If you change the unit, not only these value will increase or decrease, but the standard deviation will increase and decrease along with it. So the z-score will always be same. In fact, the z-score, the standard deviation has the exact same unit as the original data's unit, so that if you divide, the units cancel away. So you get this value which is without a unit. Okay? And therefore, these are something that doesn't change with units, which means it's something that you can believe. Right? Now, moreover, there's something called Schwarz inequality that can be shown to prove. And that's just going too much, so I'm not going to do it, but the thing called Schwarz inequality can be used to show that this value will always be between 1 and -1. With equality, it can only reach 1 if x and y are completely linear. Like there's no error, it's always a fixed relationship between them. Okay? So if the scatter plot is entirely on a straight line, if that's true, then this quantity will be exactly equal to 1. And also, if it's a straight line going this way, then this quantity will be exactly -1. So this quantity is what's called the correlation coefficient R. Okay, so there's a difference. This one is called covariance. This one's covariance. And this one is called correlation coefficient. Now there are other ways to write this. Since sigma x and sigma y are constants, it has nothing to do with the index I, which is used for the summation. You can rewrite this as covariance, the old covariance of x and y, and you're dividing this by the standard deviation of x and standard deviation of y. And then furthermore, since standard deviation is the square root of the variance, and variance is the covariance of x and x, you can rewrite this as covariance of x and y divided by square root of the covariance of x and x, covariance of y and y. That makes this more symmetric. Yeah. So this is usually called R. Okay. Okay, and then sometimes you may see the formula for the covariance where they don't divide it by n, but rather they divide it by n minus 1. Why? Why would people do that?
Bessel correction?
Bessel correction, yes. If what you have here to estimate the population covariance of two random variables x and y cannot be obtainable, or you don't have it, you just have a sample, then same story, the sample won't be a good approximation. You have to modify it by n minus 1, and then becomes a better approximation. Okay, so there's also Bessel correction applied to the covariance as well. So if you're reading some proofs, or if you're watching some online video and you see the instructor dividing by n-1, that just means that the person is working with a sample rather than the entire population. Right?